Hello, science enthusiasts. Today, we're venturing into a world where near-infrared spectroscopy meets machine learning. Here, 3 neural networks team up to decode the complex light spectrum in chemistry, helping us predict the composition of a drug. Our journey begins with the explainer network. Think of it as the code maker. It looks at the NIR spectrum from a solvent sample and translates it into a digital code. This code carries essential information about the properties of the solvent. It's then passed to the next members of our AI trio, the reasoner and producer networks. Next up is the reasoner network, our AI detective. It takes the code from the explainer network and the original spectrum, using them to infer the ratios of 10 different components. It makes the best guess based on the clues at hand. Lastly, we have the producer network, our spectrum printer using the code from the explainer, and either guesses or the true component ratios. It prints 2 new NIR spectrums. One is a reconstructed version of the original, while the other is a freshly generated spectrum using the true ratios. To ensure our system is always learning and improving, we use a measuring known as losses. They're like report cards, telling us how well the networks are cooperating. The inference loss quantifies how well the explainer and the reasoner work together to infer the component ratios. The generation loss measures how well the explainer and the producer jointly worked to generate a new spectrum like the original spectrum. Lastly, the reconstruction loss quantifies how well the producer and the reasoner communicated to reconstruct the original spectrum. Looking deeper into these losses, we uncover the core principles behind how our system learns. Each loss plays a critical role in shaping 3 unique errors: the explainer error, the reasoner error, and the producer error. These errors are the guiding stars for our system, indicating where each network needs to improve. The explainer's error is computed from the sum of the inference and generation losses, subtracted from the reconstruction loss. This offers us insight into how accurately the explainer network encodes the spectrum. The reasoner's error comes from the sum of the reconstruction and inference losses, subtracted from the generation loss. It highlights the ability of the reasoner network in making the best guesses about the component ratios. Finally, the producer's error is determined from the sum of the generation and reconstruction losses, subtracted from the inference loss. This error guides us on the quality of the NIR spectrums produced by the producer network. But how do these networks improve? That's where backpropagation steps in, a fundamental method in machine learning. It calculates the gradients of these errors with respect to the parameters of each network. These gradients essentially point out the direction that will help reduce the error. Think of it as a feedback system. By analyzing these gradients, we can see how we should correct each model's parameters to reduce its corresponding error. The explainer's parameters are adjusted to reduce the explainer error, the reasoners to reduce the reasoner error, and the producers to reduce the producer error. In this way, each model gets its own individualized learning experience, increasing the overall effectiveness of the system. This customized adjustment of network parameters using backpropagation helps in enhancing our system's efficiency and learning capacity. It's like a personal training for our networks, ensuring each one learns from its own mistakes and constantly improves. The objective of this learning process surpasses traditional supervised learning methods. Instead of using labels to calculate loss from predictions, the models indirectly learn to predict through their internal communication in the architecture. Consequently, this method reduces dependency on the training data.